In this segment, we will integrate functions which are continuous, but they are only given at discrete data points. Specifically, we'll talk about using the trapezoidal rule with unequal segments. So let's suppose you are given a function which is given at x0, x1, all the way to xn, and somebody tells you to go ahead and integrate this function from x0 to xn. And it's not necessary for it to be integrated from x0 to xn. They may ask you to integrate it from some point to another point. Those points may not be the ones which are also not given to you. And we will look at that through an example. But for the sake of simplicity, let's suppose somebody is giving you the value at these n plus 1 data points and wants you to integrate from x0 to xn. So how would you go about doing so by using trapezoidal rule with unequal segments? Is simply to say that, hey, I'm going to approximate the function going from x0 to x1 by a straight line, then x1 to x2 by another straight line, and find the area under each of those straight lines, which that area representing a trapezoid. So you're basically applying the trapezoidal rule, single application trapezoidal rule, to find out what the area under the curve is. So what we're going to do is we're going to break this up into n segments right here, all the way up to the last one, which will be this one. And we're going to find out, we're going to approximate each of these integrals by using the single application trapezoidal rule. So in this case, it will be x1 minus x0 times the value of the function x0 plus the value of the function x1 divided by 2. This is the single application trapezoidal rule where you're finding the average value of the function at the two endpoints and multiplying by the width of the interval. And we'll continue to do so all the way to the last one, which will be xn minus 1 times the value of the function at xn minus 1 plus the value of the function xn divided by 2. So if we were going to now try to write this in terms of a summation, you can see the pattern there in each of these single application trapezoidal rules. So I can say, hey, this is summation I is equal to 1 to n, let's suppose, and then this will be xi minus 1 here, while here it will be f of xi minus 1 plus f of xi divided by 2. So that's what the end result turns out to be. So in fact, I should have changed this into approximately sign, because now we're applying the single application trapezoidal rule. So let's go and look at through this example. Here we're asked to find out what the displacement is between 11 and 17 seconds. So we're going to take the velocity which is given to us at these different times, and we're going to find out what the distance covered is from 11 to 16 seconds. So what we got to figure out is that, hey, how can we use this data to be able to do so? Now keep in mind that we can now break this up into two integrals. We can go from 11 to 15 v sub t dt plus 15 to 16 v sub t dt. And somebody may say, hey, why did you do that? Is because we're given the value of the velocity at 10, then we're given the velocity at 15, and then the velocity at 20. So the only way we can break it up so as to apply the trapezoidal rule with unequal segments is to let one integral go from 11 to 15 and the next integral to go from 15 to 16. And by doing that, we'll be able to apply the trapezoidal rule with unequal segments. Now, what's going to happen is that we can approximate this now by applying the single application trapezoidal rule on this one, single application trapezoidal on this one, which will be 15 minus 11 times the velocity at 15 plus the velocity at 11 divided by 2 plus it'll be 16 minus 15 times the velocity at 15 plus the velocity at 16 divided by 2. However, what we got to understand now is that we do know the velocity 15, which is given in the table itself, but the velocity at 11 and velocity 16 are not known to us. So we have to somehow find out what these approximate values of velocity are, 11 and 16, to be able to move forward. And what we can do is, since the trapezoidal rule of unequal segments is dependent on saying that, hey, we're going to draw straight lines going from one segment to another, the best thing to do is, in order to find these velocities which are not given to us, is to simply use the straight line approximation to be able to do so, or what we may call as linear interpolation to do so. So if we want to find the velocity at a particular time, we know that, hey, we have this particular formula, which is actually the formula for a straight line, which is given by, hey, if you know the velocity at 2 points, t1 and t0 and t1, then you can find the velocity at any point between t0 and t1 by using this formula right here. This is the formula of a straight line. You can use y is equal to mx plus b type of formula as well, but that's going to give you the same result. However, in that case, you'll have to solve two equations, two unknowns, but this is a direct way of doing so. So now we want to find the velocity between 10 and 15 seconds, so as to be able to find the velocity at velocity 11. So velocity of expression will be given as velocity at 10 plus the velocity at 15 minus the velocity at 10 divided by 15 minus 10. So your t0 is 10, t1 is 15 in this case, in this formula here, t minus 10 here. And this particular velocity profile will be valid between 10 and 15 in the time domain. Now if we want to find the velocity at 11, all we have to do is to put t equal to 11 there. Velocity at 10 is given as 227.04. Velocity 15 is given as 362.78. So let's go and put these numbers here from the table which are given to us. Now time is 11 minus 10, and this number here turns out to be equal to 254.19 meters per second. So similarly, we're going to find the velocity at 16. So we've got to find out the velocity at 16 now. So we're going to choose the values of the velocity at 10 and 15 and 20 to do that. So we'll have velocity 15 plus velocity at 20 minus velocity at 15 divided by 20 minus 15 times t minus 15. So we've chosen the velocities of 15 and 20 to find the velocity 16. And this particular expression will be valid between 15 and 20. So if we want to find the velocity at 16, that will be the velocity at 15, which is 362.78. The velocity at 20 is given as 517.35. This is the velocity at 15, divided by 20 minus 15 times 16 minus 15. And this number here turns out to be equal to 393.69 meters per second. So now what we have is we have the velocity at all the points which are given to which are needed in order to find the approximate value of the distance covered from 11 to 16 seconds. So going back to that one, then we have the integral going from 11 to 16 of the velocity is approximately given as this expression which we had already written is the velocity at 11 plus the velocity at 15. So this is the average velocity at 11 15 multiplied by the width of the segment, plus we go from 16 minus 15 divided by 2 times the velocity at 15 plus the velocity at 16. So we already had this number from the table, but we did not have these two numbers which we had to interpolate to find from the table. So now we have all of these numbers. So the 15 minus 11 divided by 2, velocity at 11 is 254.19, which we just found out by interpolation. Velocity at 15 is 362.78, which we found by from the table. Then we have 16 minus 15 divided by 2. Velocity at 15 is 362.78, and we add the velocity at 16, which is 393.69. And once we do these calculations, we get 1612.69 meters. And that is the end of this segment.